Swayam Prabha. Digital India. Educated India.
All right, let's get started. To kind of recap what we have done in the last class, we have at last started looking at some experiments and experimental data, briefly at least. So we have primarily looked at third order responses because we have kind of accepted that that's probably the most relevant kind of nonlinear response, which can give us some interesting insights into processes happening in materials. We have discussed one, let's say, widely employed technique called pump probe. We have also looked at two pulse photon echo. So both of them are two pulse experiments. Interestingly, one of them, pump probe, particularly gives access to population dynamics exclusively. You have no information about coherence. Photon echo, on the other hand, gives you exclusive access to coherence lifetimes. You're measuring dephasing lifetimes. Particularly when you have the condition where we have also discussed homogeneous and inhomogeneous contributions to dephasing process or coherence loss in systems. And we have noted that in the limit where my inhomogeneous broadening is dominant, you will see that the photon echo signal will decay as a mono-exponential function with a decay rate corresponding directly to the pure dephasing rate. Okay. Now, we have kind of introduced homogeneous and inhomogeneous broadening sort of in a very, I would say even qualitative way, maybe quantitative. So I want to go and dig deeper into the microscopic theory of dephasing a bit. Even this is what I'm going to do is kind of at a more introductory level, basic level. If you want more advanced treatment, I can give you some notes. This is based on seminal work from Kubo and Anderson-Kubo theory. Anderson and Kubo independently developed this way back in this. I think the Kubo's paper is from the 60s, if I remember correctly. So I'm not going to go into the entirety of this because then I start getting into dissipation fluctuation theorem and quantum regression theorem and so on and so forth, which kind of gets, initially I wanted to do that, but I thought, okay, that's going to get extremely challenging to kind of introduce it in one class and have you assimilate that. So I'm not going to go into that, but I'm going to give you a more deeper sense of what's happening. And later on, if you're interested, I could provide more additional details. All right. Microscopic theory of dephasing. Let's go back to linear response. I'm going to write my linear impulse response function. I can write in different forms. I'm going to write it as it was even before we are able to write it down in terms of correlation functions. So that will be mu t, mu of 0, rho equilibrium. Right, so this is, we can then write this out as the difference between the two correlation functions, but this is even before that. So let's go back to the old form. So in a two-level system, of course, this becomes simpler. This simply becomes mu 1, 0. This evolving with time, mu 1, 0, and time, and rho 0, 0. Everything is in the ground state, kind of goes. Okay, typically my dipole, evolution of my dipole, it's like any system evolution. So it's going to, as it evolves, it's going to gather some kind of phase, dynamic phase. So I can write this to be some 0 e power minus I omega t, where omega is simply the energy difference. Remember, this is in the absence of the bath, in the presence of the bath. We have already done this. I'm going to introduce in a slightly different way. It's probably more meaningful. So what happens? Again, going back to the physical intuition, in the presence of the bath, the system is interacting with the bath. What changes of the bath? The thing that can change is my transition frequency. You can kind of think of it that my energy gap is fluctuating. That is the most simplest way to think about it. So I could say my omega now becomes omega of t. The frequency fluctuations. Now, if I have something like that, then if I write my equation of motion, like evolution of my dipole moment, I can write this now omega of t mu 0 1 t. If I integrate this, I get the time evolution of my dipole to be e power minus I integral 0 to t d tau omega of tau. So in the last class, I kind of said the part which is most relevant is this phase acquired as we propagate with my interaction. So that's the part here. Because of frequency fluctuations, you have to integrate over all possible fluctuations to get your overall phase acquired. Of course, this. Okay, so what can be the specific kind of form for my omega t here, which will tell you the overall phase acquired within certain time scale? Let's do that. We can kind of say my omega of t is some mean value plus delta omega of t, where delta is small. I'm kind of saying, okay, if I look at my omega, the fluctuations around it is too small around that value. It's time. Remember, these are fluctuation, which means the time evolution is by nature stochastic, right? So you'll say my omega now is a time average mean of my omega t. And if I average my fluctuations over time, this will be, if I average my fluctuations over time, 0. Okay. That's my consideration, just reasonable. Considering this, now linear response now, if you remember, it has a term of this kind. And if I make substitution from the previous slide, I'll get this to be multiplied by average exponential minus I integral 0 to t d tau delta omega tau. So one could solve this particular integral here. So you could kind of calculate this using what is referred to as the cumulant expansion. Without going into too much detail, what cumulant expansion is, if you're interested, again, please come to me. I can explain to you. I can calculate this exp minus I integral 0 to t d tau delta omega of tau. Basically, the overall phase acquired will be 1 minus I integral 0 of t dt, something which goes linear delta omega, then of course something which goes square quadratic with delta omega, sorry. so on and so forth. Remember, going back at the end of the day, whatever I highlighted in this green here or whatever I'm calculating, this is your damping term at the end of the day because of bath interactions. So this has to be equated to some form of e power minus g of t, where g is your damping. G of t is telling you the functional form of your damping, right? This is the oscillating part and this is the damping part. So it has to be of the form of e power minus g of t. Okay, so we can equate this to some kind of damping term. So remember this part here. We'll come back to that. So I should be able to write my e power, sorry. So my e power minus g of t to be some 1 minus g of t plus half g square of t, so on and so forth. Now, if I can expand g of t itself, as noted earlier, as some kind in the powers of the delta omega, right? So it's some kind of 1 minus g1, sorry, this is, I'm making mistakes. It's g1 of t, which is going in terms of delta omega plus g2 of t, which will go as delta omega, plus so on and so forth. Basically, you combine this, we know this will be 0. Combining this, you will see my delta omega tau prime, delta omega, I'm sorry, I'm making mistakes today. That's not what I want to write already. Okay, so now I should be able to write my g of t, combining these two considerations, to be half integral 0 to t, integral 0 to t, d tau prime, d tau double prime, delta omega of tau prime, delta omega of prime, plus something of the order of delta omega cube, but that will be small, so we can ignore it for now. I could even make a transformation, sort of a transformation of the space here, and I can kind of replace my delta omega tau prime to tau double prime to delta omega tau prime minus tau double prime delta omega 0. So you're kind of taking correlation only with respect to the fluctuations at time 0. Okay, so think of these correlations. I can show you some kind of visual representation of that. Let's see if I can share. Yes, I can share. Don't worry about the amplitude of fluctuations, but think about the nature of the fluctuations. And what you see here is there's two kinds of fluctuations. One, relatively slow fluctuations in blue. They're going slowly. So it's just a quick Python's code to kind of show that when I have fast fluctuations, you can even take this time series and try to calculate a time correlation. It'll go to 0. This will be close to 0. Whereas if I take this blue curve, which is kind of slowly varying fluctuations, you can kind of see, oh, at least some kind of time scale, you will have certain non-zero correlation, right? Okay, so that's all I wanted to show here. So as I said, when I have very fast fluctuations, fast or rapid fluctuations, I'll get my correlation just replace with some time 0 will be a delta function. If I have slow fluctuations, it's kind of reasonable to consider that this correlation function is going to decay in time in some fashion. Like if I take a Gaussian distribution for this statistics of this fluctuation, for example, I could kind of see that the correlation will decay exponentially, right? So it's not inconceivable to say that in the limit of slow fluctuations, this is going to be some kind of exponential decay function with some correlation time tau c and some amplitude delta square. Okay, delta is a fluctuation amplitude and tau c is some kind of correlation function. This can be derived actually. It's a bit more detailed derivation, but it's also kind of physically makes sense to kind of expect such kind of response. If I consider that this kind of scenario of slow fluctuations, then I will get my G function in general for the general case to be delta square tau c e power minus t over tau c plus t over tau c minus 1. And this is referred to as the Kubo line shape function. Kubo. And you can kind of see in this case when you will have your product of delta and tau c much smaller than 1, there has to be some delta somewhere here. I missed it. I will probably update this in my notes later. I think I got this wrong. This final expression, there has to be a delta somewhere inside, but that's fine. So under the assumption of my product of delta and tau c much less than 1, basically saying that my correlation time scale is extremely short when I have this rapid fluctuations, will be close to 0. Then you can show my G of t is basically t times some gamma. In fact, you can show this gamma to be actually this. And this is what is referred to as the homogeneous limit. And in fact, gamma happens to be your dephasing rate. Rapid fluctuations. On the other hand, if I have slow fluctuations, I can have both of them. I could have fast fluctuations as well as slow fluctuations. I have slow fluctuations only. You can see that G of t is half delta square t square. We have already kind of spoken about this. We just considered that there is we just considered that this is the form of my correlation. I consider this to be form of the correlation. Of course, if my tau c is extremely short, then it becomes automatically a limit of fast fluctuations. So it's quantified by my correlation time at the end of the day, right? So I have a parameter that I can change. If I make it almost close to 0, then okay, then it's a fast fluctuation limit. If it is slow, then I make it large. So that's why we are able to get, in this case, access to both the limits, sort of. But this expression itself is generally valid. So even in the case where I have homogeneous, inhomogeneous contribution, there are fast fluctuations as well as slow fluctuations. Then you kind of have both these contributing. Now you might ask, okay, how do I know when I have these fast fluctuations? When do I have my slow fluctuations? At the heart of it, it's all related to the kind of bath I'm dealing with, right? So it has to be somehow related to some kind of property of this bath. And can we kind of get that understanding of what kind of bath I'm dealing with? The answer is yes. Again, it's pretty extensive, non-trivial derivation. Kubo did it. So I'm not going to do that right now, but I'm going to give you kind of framework over which this can be done. So just to get a picture, remember the way you're writing down the fluctuation is considering system bath interaction. So your effective system Hamiltonian is no longer what is called H naught, but you have your system plus some bath plus a system bath interaction, right? So your system bath interaction is some kind of, it's not some kind, it is a convolution of system and the bath operator, bath interaction operator, where your bath interaction operator can be written as sum over K, some interaction strength, coupling strength, times some bath operator plus GK star BK. Okay, so if you think about this, my system bath interaction, if S is my system thing, then I can write this as GK excite a bath mode and kill a system mode, or kill a bath mode and excite a system mode. That is system bath interactions, like, and this is a term which leads to these small fluctuations in the thing. And in general, the bath also evolves with a dynamic phase. Has its own evolution. Overall, at the end, the way to deal with it, if I have this bath operator, usually you calculate the time correlation of this bath interaction parameter, which gives you access to everything else. And it can be shown, I'm not going to show this now, it can be shown that in the continuum limit, this leads to a correlation, a bath correlation function of this form. The reason I'm writing down is because it gives you an access to an important parameter, J of omega, of a complex looking equation, but bear with me. It's not totally inconceivable. Minus I sine omega t, where your J here is what is called, J is what is called spectral density of the bath. And that is the key here. It's the spectral density of the bath. Okay. And this correlation function itself has to think about it. The real part of this is related to some kind of fluctuation, and the imaginary part is associated with dissipation. And this is where the fluctuation dissipation theorem comes in. I'm throwing in a lot of words. If you don't understand it, it's fine. It's something that is at the heart of dealing with system bath interactions, quantum dynamics. Even if you're interested in something like emerging quantum computing applications, so on and so forth, this is really at the heart of it. If you want to kind of, this kind of applies to, in a very generic framework, to any kind of quantum system, right? So it so happens that that spectral density of the bath is the critical aspect, and depending on different properties of the bath, you can get different kind of behavior. For example, it can also be shown that that spectral density has a very specific form. It is dependent on the frequency itself. That's a very important thing. Dependent on frequency with some efficiency. But the important part is omega c is the frequency of the bath mode, but that doesn't matter. The most important thing is this S parameter. So if you can see here, your J, your spectral density, can either be linear, superlinear, or sublinear with respect to the frequency of your oscillator, okay? And depending on that dependence, you can get what is called ohmic behavior of the bath. Ohmic behavior is when you have linear dependency. You can have sub-ohmic, where S is less than 1, or you can have super-ohmic, where S is greater than 1. Simple demonstration of what it will entail. I just want to show taking spectral density super-ohmic, sub-ohmic as ohmic, and I want to show how the coherence decay kind of looks like. Anyway, simple thing is, if I have usually super-ohmic behavior, your access, your spectral density increases nonlinearly at higher frequencies. And so what you'll have is your probability for very random and very fast fluctuations increase very rapidly. And so when you're typically having a bath which is super-ohmic, then you are in this limit of very fast fluctuations. Okay, and for example, phonons are super-ohmic bath. In fact, there your S is, if I'm not wrong, S is around 3. It's cubic on the frequency. Okay, the spectral density scales cubic with frequency. On the other hand, if I have disorder in the system, like side-to-side disorder in the system, typically that is sub-ohmic. Okay, so sub-ohmic. So you'll have disorder in the system. Think about it, right? So I'm going on my excitation exists. If I want to, if I'm staying here as an excitation and my lattice is all surrounding, the phonons are everywhere and they're kind of hitting me from all directions. So I'm going to be subject to very fast fluctuations because the phonons are all around me. But if there is side-to-side disorder, as a localized excitation, I should be able to first access that site to experience a side-to-side fluctuation, right? So it can kind of not inconceivable think that side-to-side disorder, like disorder in a lattice, you need some time for the photoexcitation to access those kind of fluctuations than, for example, fast fluctuations coming from phonons. Kind of makes sense intuitively. So the takeaway message is that your bath can come in different forms. Sometimes the bath will have large spectral density to drive very rapid fluctuations. And when you have such very rapid fluctuations, you're in the so-called homogeneous limit with an effective dephasing rate, which is mono-exponential. Whereas if I have, if I could have a bath where my evolution is, or the fluctuations are happening at much slower time scale, which means my correlation time scale between frequency fluctuations at 2 different points is non-zero or is finite. Okay, we have the thing. So here I kind of chosen 3 S's. Frankly, it's kind of a bad plot because if you look closely, the blue S equal to 0.5, it's almost flat. It doesn't almost change on it. It's because it's very small. Whereas if I go to super-ohmic at S equal to 3, you have very rapid increase. And here I calculate my coherence decay for 3 different conditions. And you see very rapid fluctuations. It decays at extremely fast time scales, boom, right? But it's mono-exponential. Whereas the form of the decay will change as I go with slower fluctuations. Okay, make sense? Okay, good. So with this in mind, let's go back to our friend. Who's our friend? 2-pulse photon echo. So let's go back to 2-pulse photon echo with this understanding of different things. We're kind of getting an origin, a microscopic picture of where the slow and fast fluctuation arise. So remember your photon echo, the impulse response function for your photon echo, it's newer word, R of 3 is proportional. I'm writing the final equation, e power minus omega 0, 1, tau 1 minus tau 3, e power minus gamma 0, 1, tau 1 plus tau 3, e power minus tau 1 plus tau 3 square delta square over 2. So this is your, and I kind of explicitly write down both possible contributions, slow as well as fast, fast as well as slow, explicitly. And you know my response or the signal that I'm measuring, let's call that signal S will be in time, the interferogram that you're going to measure will be integral 0 to infinity d tau 3 p of 3 tau 1 tau 3 square. Remember, this is a function that one could simulate. I'll show you some forms of the nonlinear polarization extracted from this impulse response function. And I could find an analytical solution for this kind of response functions. It can be shown, but S of tau will be exponential minus 4 gamma 0 1 tau minus gamma 0 1 square over delta square, error function minus delta tau plus gamma 0 1 over delta. I'm not deriving this, I'm giving this to you, but the curious thing is that you have this error function, just a functional form which kind of emerges. Now, let's take two limits. The two limits are pretty nice, pretty easy. So let's say if I have my delta much less than gamma 0 1, you will see that my system, the intensity of or the measured signal will be proportional to e power minus 2 gamma 0 1 tau. And on the other hand, if my delta is much greater than 0 1, then S of tau will be proportional to e power minus 4 gamma 0 1 tau. So in both cases, where I have my fast fluctuations are always dominating, or when I have my only slow fluctuations dominating, in both cases, the signal that I measure with photon echo will decay exponentially with a rate given by the pure dephasing. So it's all only determinant on my fast fluctuations, right? In both cases. Now you will ask, why should we have both fast and slow fluctuations at the same time? Is there a reason? Anybody can answer that? Why did I write both gamma 0 1 as well as my delta there? I kind of, in the previous few slides, I kind of said, hey, I can have, if I have slow fluctuations, I'll have this, but I can write this using one common delta, right? And so depending on the correlation time, I can have fast or slow, right? But here I explicitly write down both my fast as well as slow fluctuations. Why is it the case? Why did I write that? Two, what? No, it's nothing to do with fields. It's everything to do with the system that we are looking at. You need not have one singular bath. You can have different kinds of bath coexisting. You could have a system where I have phonons as my bath as well as static disorder. I can have both of them, right? In the case where my static disorder is everywhere around me, is the dominant one, then I'll have predominantly slow fluctuations, fine. Where my phonons, for example, they don't scatter because they don't care about electrons for some reason. Then I'll have the limit of inhomogeneous broadening. On the other hand, I can have this other limit where I'm dominated by very fast fluctuations. It's not that you will have this digital thing, you will always have contributions from both, right? You could have a material where there is substantial static disorder, right? And you can have independently a system where the static disorder is minimal, but it's not completely absent. It's kind of inevitably present, okay? The takeaway message is that in either limit, sort of inhomogeneity is kind of removed by design in the experiment, from the experimental response. Sometimes it's counterintuitive. I'm like, okay, if I have inhomogeneity dominating, why the hell it is being removed, right? It's being removed because of the rephasing character, if you think about it. let's keep thinking about that. That's a very critical point. I'm kind of highlighting something which I found extremely kind of confusing when I was studying, trying to learn this properly. I'm like, the system is dominated by inhomogeneity, only slow fluctuations. I measure a response, a 2-photon response, a 2-photon echo, 2-pulse photon echo. Then even though inhomogeneous slow fluctuations are the dominating part, it's much, much stronger in amplitude. It doesn't matter. What I'm measuring is just the fast motional narrowing or homogeneous broadening. Okay, that's because, again, fundamentally of the rephasing character. In either case, what the rephasing does is that it recovers the phase, and that's at the heart of it. Okay, and it so happens if I have slow fluctuations, system has a memory of where it comes from, where the previous phase is, which means when I try to rephase it, it can go back exactly and recover the phase. On the other hand, if I have very fast fluctuations in the system, when I try to do the rephasing, it can never go back because it has lost the memory. That is at the heart of the argument. In fact, going back to the condition where I have comparable fast and slow fluctuations contributing, you will see that this error function here is going to contribute. And we have plotted this error function of this kind, with time, it will grow, actually, okay? So there is something here. So if I have pure inhomogeneous broadening, kind of without any dephasing, let's say, I should be able to recover my thing, go back exactly, okay? So I should be able to reach a maximum. So my homogeneous broadening is trying to destroy coherence, but with inhomogeneous broadening, I could kind of recover something back. It's kind of very interesting, right? You can use disorder to recover coherence, which is kind of very fascinating avenue for research. I will not talk about it right now, but it's kind of very interesting to kind of see how we can use correlated disorder. There should be some correlations. You could potentially recover coherence, which is interesting in itself. So because of this reason, in some cases, I will show you some, again, hopefully this will work. So I calculated the echo intensity as a function of time. And in both, let's say, where it's dominated by homogeneous or inhomogeneous broadening, you kind of get a similar kind of response. So the different amplitudes because I have not normalized. But when I have both of them kind of comparable, you see actually an increase in the intensity. I see that the maximum point that I have is not exactly at time 0, but at a much later time. That's because I'm at later time, I'm able to rephase properly when I have these two competing processes. Professor Krishna asked for an experiment. Let's see an experiment. This, by the way, is one of the early, oh, sorry, I need to share that. Share, PowerPoint, open. Okay, so this on the left, in fact, happens to be one of the early photon echo done on 2-dimensional excitons and gallium arsenide, aluminum gallium arsenide quantum wells. And you see a nice decay here. Of course, it's convolved with your pulse width. We're doing it with picosecond pulses. Now we have 10 femtosecond. They still saw beautiful signs there. And I want to kind of point out that similar kind of response is seen in magnetic resonance. But what I want to show is this. This is, again, early photon echo study on light harvesting complexes found in photosynthetic system done by Graham Fleming in Berkeley. And you see that you can see this kind of shift, and they plot this shift here as a function of time. I'll come back to this time later, but you would see some kind of response of this kind where the system has a maximum at a point much later. That's because you're able to recover or rephase things properly at much later time. Now let's make our life a bit more complicated. Let me hide floating controls. Add this. So I'm going to give an analogy. These are called lens kind of analogies because we are all optics people. We can kind of talk about lens analogies. Yeah, go ahead. Yes, I mean, the refacing is happening all the time. It's just that when you have these comparable at some balance, you will see that the maximum of the signal happens at a bit later than time zero. So the system is not completely losing coherence to begin with. So the reason, let me explain this, so hopefully it'll become clear. So let's say I'm looking at my phase that I accumulate as a function of time, okay? And let's say for one of my chromophores, I'm looking at fluctuations of different kind. This is, let's say, my tau1, and this is tau3. My system evolves, there is some increase, and then I come with my second pulse, a third pulse rather, and you have the refacing part. Now, this is just one chromophore, if I might call it. I can, or kind of within one homogeneous, there's no homogeneous line width, let's say one set of chromophores. And then I can have inhomogeneous broadening of this, and there can be another sub-ensemble which will have slightly different response, so on and so forth. But all of these sort of come back and meet at the same point. They kind of reface perfectly. Okay. Now, if I had some kind of homogeneous broadening, the way to think about it is that I could have in the same, on top of this, some line of fluctuation around it. Okay. I come back, this will come here, this guy go somewhere else. It's like aberration in your lenses, right? It will not focus at the same point. It will focus somewhere else because there is stochasticity, very fast fluctuations driving this, unless you're at time zero. You start the coherence and measure it immediately. You measure the response. So only at time zero, it will be maximum. After it will decay when you have stochastics. But when I have the both correlated, let's say, some kind of correlations in the system, there could be some sub-ensemble where you could recover some degree of coherence at a time which is not exactly at zero. I can't represent that. Or at least I have not figured out a way to represent that, sorry. Exactly. Now we can here in this case, your tau2 is 0, remember, because there is only 2 pulses. I could make now a 3-pulse experiment. If I make a 3-pulse experiment, then I'll have tau1, tau2, and tau3. Let's say my phi evolution, it evolves in T1, tau1, because it's looking at coherence. Remember, in 3-pulse experiment, when I come with second excitation, what do I create? I create a population. Once I create a population, there's no phase attached to it, right? It's a population projected. There's no coherence there. So the phase will remain constant, and then it can die down, right? So you can rephase with the third interaction. Very nice. But let's say there are fast fluctuations, but also when my population exists, my population can also be subjected to fluctuations. The population itself can have some energy fluctuations. So it's not inconceivable. This is called what is called spectral diffusion in spectroscopy. I could have things like that happening. And that case, even in 3-pulse echo, even during the population time, I could have evolution. Okay. So basically, if I wait long enough, then even if I start out with a condition where there is some degree of inhomogeneity enabling you to recover the coherence, after some point in time, waiting time of the population would evolve so randomly that it can never recover back. So you kind of do the same experiment as a function of time. Initially, you might be able to start, if I write my response, you might be starting with some response like that. But as you wait longer, so this is at some tau 2 equal to 0, if I go to tau 2 greater than 0, it could become something like that. And that's because I could have additional stochasticity coming from the population evolution. Okay, so now I'm kind of putting all of this, a lot of things there, in a very qualitative, semi-intuitive kind of way. You kind of write it down all in math. Please go and think about this, because these are one of the most challenging things, I would say, in spectroscopy, in these kind of spectroscopies. And I want to show this data again. Doesn't show up. Yeah, so this by Graham Fleming's group, this one is looking at that peak shift as a function of waiting time, the population evolution in photosynthetic system. In the beginning, they had like the peak was shifted by about 25 femtoseconds. They wait long enough, that peak kind of goes back to 0. That's because the population evolves in that time scale. It's a very fast time scale. Think about this. The very fast time scales. And this kind of lets whatever this rephasing character which is there at a later time is completely taken up, and you're kind of going back to your motional narrowing or homogeneous limit. Okay. If you're kind of interested more on this, I have written a paper in 2020 on this topic. We kind of did a very extensive analysis of time evolution of spectral response under stochastic scattering. Okay, the funny part is that stochastic differential equations are developed extensively in the context of economics. It's called Ito calculus. So money happens to have stochasticity, and apparently it's very nice. Here we use Ito calculus to be able to calculate the response functions, the G's, the cumulative expansion, using Ito calculus to get more accurate representation of the system response. And what we have found is that not just the inhomogeneity is kind of evolving, the homogeneous line width is also evolves in these very fast time scales, all because of stochastic evolution of the population. The takeaway that I want to emphasize is that the stochasticity, the random fluctuations, is not only affects the coherence part of the thing, but also in the presence of the population, you can have very strong scattering, which stochastic behavior, which gets into it. Okay, fair enough.